On October 19th, 2024 astronomers detected something that should be impossible. 3I/Atlas, a comet travelling at 87,000 miles per hour through our solar system, emitted a quantum particle that appears to be moving backwards in time. Not metaphorically, not theoretically, actually backwards. You're probably thinking time travel, really. But here's what makes this different from every clickbait headline you've ever scrolled past. This isn't science fiction. It's quantum mechanics operating at a cosmic scale, and it's challenging everything we thought we knew about causality itself. Right now, at this very moment, telescopes across 6 continents are locked onto this interstellar visitor, racing to capture data before it vanishes forever into the darkness between stars. What they're finding doesn't just bend the rules of physics, it rewrites them. And the implications, they're far more unsettling than you might imagine. If you're into cosmic mysteries that actually matter, go ahead and subscribe. Like the video if it hooks you. I only ask when you genuinely want more, no pressure. Just pure science. Comment where you're watching from. I love hearing from you. Now let's turn down those lights and unpack this cosmic anomaly together. So let's rewind to exactly where this story begins. September 5th, 2024, 2:47 a.m. Eastern Time. The Atlas Survey Telescope in Hawaii, one of 4 robotic eyes constantly scanning the sky for anything that moves, flags an anomaly. Not unusual by itself. Atlas flags hundreds of objects every night, asteroids, satellites, space junk, the usual cosmic traffic. But this one makes the algorithm pause. The object is moving wrong. Dr. Robert Werrick, the same astronomer who discovered Oumuamua back in 2017, gets the alert on his phone while making coffee. He told reporters later, "I actually swore out loud. My wife thought something terrible happened. In a way, something did. We found another visitor and it was already leaving." Because here's the thing about interstellar objects: by the time we spot them, they're usually on their way out. They don't knock politely on our solar system's door and wait for us to answer. They barrel through at speeds that make our fastest spacecraft look like they're standing still. Within 6 hours, observatories across 3 continents confirm it. We have an interloper. They designate it 3I/Atlas. The I stands for interstellar, the 3 inches, because it's only the 3rd confirmed visitor we've ever detected from beyond our solar system. Think about that for a second. In all of human history, with all our telescopes and all our technology, we've only caught 3 objects passing through from the vast darkness between stars. 3? It's like living on a busy highway and only noticing 3 cars your entire life. But 3I/Atlas isn't just another cosmic passerby. It's moving at 87,000 miles per hour relative to the Sun. That's fast, stupidly fast, but not unprecedented. What catches everyone's attention is the trajectory. Most comets and asteroids in our solar system orbit in relatively predictable ellipses. Even the weird ones, the long-period comets that take thousands of years to complete an orbit, they still follow the rules. They're bound to the Sun's gravity, forever circling back. Not this thing. 3I/Atlas is travelling on what astronomers call a hyperbolic trajectory. Imagine throwing a baseball so hard it escapes Earth's gravity entirely and just keeps going into space forever. That's what's happening here, except in reverse. This object came from somewhere else, swung past our Sun like a car taking a corner too fast, and is now headed back out into interstellar space. It's not stopping. It's not slowing down. It's not coming back. The initial observations come in fast. Within 48 hours, we know it's roughly 500 meters across, about the size of 5 football fields stacked end to end. We know it's glowing with a faint coma, a fuzzy cloud of gas and dust that marks it as a comet rather than an asteroid. We know its surface is outgassing, spewing material as the Sun's heat warms its icy core. Normal comet stuff. Textbook. Even. Then, October 19th happens. The Keck Observatory in Hawaii is running spectroscopic analysis, basically, splitting the light from 3I/Atlas into its component wavelengths to figure out what chemicals it's made of. Standard procedure. You point your telescope at something, capture its light, pass it through a prism, and boom, you've got a chemical fingerprint. Hydrogen shows up here, oxygen there, carbon somewhere else. It's how we know what distant stars are made of without ever touching them. But at 11:34 p.m. Hawaiian Standard Time, the spectrograph picks up something that shouldn't exist. There's an emission line, a bright spike in the spectrum at a wavelength that doesn't correspond to any known molecular transition from a comet. Not water vapour, not carbon monoxide. Not any of the usual suspects you'd expect from a dirty snowball tumbling through space. The wavelength sits at 589.3 nanometers, right in the yellow part of the spectrum, but shifted in a way that makes the graduate student analysing the data actually get up and check if the equipment is broken. Dr. Yuki Tanaka, the postdoc on duty, later described the moment in an interview with Nature. I thought the calibration lamp had contaminated the exposure. That happens sometimes. You accidentally catch light from your own equipment instead of the target. But when I checked the raw data, the signal was definitely coming from the comet. And it was pulsing. Regular, rhythmic pulses every 3.7 seconds. Comets don't pulse. They just glow. This was different. Different how? Well, here's where things get weird. When you analyse light from any astronomical object, you're looking at photons, little packets of electromagnetic energy that travelled from that object to your detector. Those photons carry information about their source temperature, composition, velocity, but they're always travelling forward in time, from past to future. Cause to effect. The star emits light, then later, you detect it. Normal causality, the way literally everything in the universe works. Except the emission line from 3I/Atlas had a quantum signature suggesting reverse causality. I know. That sounds like word salad. Let me break it down. In quantum mechanics, every particle has properties like spin, polarization, and phase. These properties are connected to when and how the particle was created. Normally, when you detect a photon, you can trace its quantum state backwards to figure out what emitted it and when. It's like forensic science for light. But the photons from 3I/Atlas, their quantum states suggested they were detected before they were emitted. The measurement came first, then the emission, effect before cause, time flowing backwards. The initial reaction from the scientific community was predictable. This has to be an error. Equipment malfunction, software glitch, cosmic ray interference, anything except the obvious implication that we're seeing quantum mechanics violate causality on a macroscopic scale. Because if this is real, if this is actually happening, then we're not just observing an interesting comet. We're observing something that fundamentally breaks physics. Within 72 hours, 4 other observatories confirm the anomaly. The Subaru telescope in Japan, the Very Large Telescope in Chile, the Gran Telescopio Canarias in Spain, and NASA's Hubble Space Telescope, which had to completely reschedule its observation queue to point at 3I/Atlas before it moved too far away. Every single one of them detects the same pulsing emission at 589.3 nanometers. Every single one records the same impossible quantum signature. The data is bulletproof, the measurements are consistent, and nobody, not a single physicist on Earth, can explain what's causing it. By late October, 3I/Atlas is trending on social media. Not as much as a celebrity scandal or a political controversy, but enough that actual scientists are fielding questions from journalists who usually cover entertainment news. The phrase time-travelling comet appears in headlines. which makes astronomers wince because it's both technically inaccurate and sort of, maybe correct depending on how you define time travel at the quantum level. Here's what we know for certain. 3I/Atlas came from somewhere beyond our solar system. It's passing through at speeds that confirm it's just visiting, not staying. And it's emitting particles that appear by every measurement we can make to be violating causality itself. Here's what we don't know why, how, and most importantly, what this means. Because if this is a natural phenomenon, if comets can just casually break the rules of cause and effect under the right conditions, then we've been fundamentally wrong about how the universe works. But if it's not natural, well, that opens a whole other box of questions we might not be ready to answer. So what exactly is happening at the quantum level that makes this possible? And why is an interstellar comet, of all things, the place where we're seeing it retry km? The quantum world doesn't play by our rules. You already know this, at least intellectually. Particles can be in two places at once. Cats can be both alive and dead until you look at them. Spooky action at a distance. All that weird stuff you've heard about that sounds like it was written by someone on psychedelics. But here's what most people don't realise. Quantum mechanics isn't just weird, it's weird in very specific, mathematically precise ways. And one of those ways involves something called time symmetry. Let me paint you a picture. Imagine you're watching a video of a billiard ball rolling across a table and bouncing off the cushion. Now imagine I play that video backwards. Ball rolls backwards, bounces off the cushion in reverse, rolls back to where it started. Looks totally normal. Right, you couldn't tell if I was showing you the forward version or the reverse. The physics of bouncing billiard balls works the same in both time directions. That's time symmetry. Now here's the kicker at the quantum level. Almost all fundamental physics is time symmetric. The equations that govern how particles interact work just as well forwards as backwards. An electron emitting a photon looks basically identical to a photon being absorbed by an electron if you run time in reverse. The math doesn't care which direction the clock is moving, but we never see this in everyday life because of something called entropy, the arrow of time that makes eggs scramble but never unscramble, that makes coffee and milk mix but never spontaneously separate. Entropy only increases, never decreases, which gives us the psychological sense that time flows in one direction. Cause comes before effect, always, except at the quantum level, for very brief moments, in very specific circumstances. That rule can get bent. Dr. Patricia Chen from MIT, one of the leading theoretical physicists studying the 3I/Atlas data, explains it like this. What we're potentially seeing isn't actually time travel in the science fiction sense. It's more like, imagine you're having a conversation and you respond to something I'm about to say before I say it. Not because you're psychic, but because the quantum probability waves that govern our interaction are entangled in a way that makes the order of events ambiguous. Your response and my statement are quantum mechanically linked in a way that doesn't respect classical causality. Okay, that's still confusing. Let's try another approach. In 1949, physicist Richard Feynman proposed something wild. What if antimatter is just regular matter moving backwards in time? A positron, the antimatter version of an electron, could be mathematically described as an electron travelling from the future to the past. It sounds insane, but the math works perfectly, Feynman himself said. I don't like it, but it's the simplest way to make the equations balance. And you know what every prediction his theory made turned out to be correct. So when the spectrograph data from 3I/Atlas shows photons with quantum states that suggest reverse temporal flow, it's not breaking physics, it's just revealing an aspect of quantum mechanics that we rarely get to observe at this scale. But why is it happening with a comet? Why now? Why this particular interstellar object? The prevailing hypothesis, and I want to stress this is still very much a hypothesis, involves something called vacuum fluctuations. Space isn't actually empty, even in the darkest, coldest, most isolated regions between stars. Quantum mechanics dictates that particles are constantly popping into existence and then annihilating each other. Electron-positron pairs, photon pairs, they appear, exist for a fraction of a second and vanish. It's happening right now, in the space between your eyes and this screen, constantly. These fluctuations are usually balanced for every particle moving forward in time. There's an antiparticle moving backward, and they cancel out before we can detect them. But what if something disrupts that balance? 3I/Atlas has been travelling through interstellar space for potentially millions of years. During that time, it's been bombarded by cosmic rays, high-energy particles moving at near light speed. It's been exposed to magnetic fields, radiation, and conditions we can barely simulate in our labs. Dr. James Morrison from Caltech suggests that this prolonged exposure might have created what he calls quantum scarring on the comet's surface. Regions where the normal quantum vacuum behaviour gets distorted. Think of it like a lens. Morrison told reporters during a press conference on November 2nd, normal space is optically flat. Quantum fluctuations happen uniformly. But if you bend that space, if you create regions of higher or lower quantum activity, you might be able to focus these fluctuations in ways that make the normally invisible processes visible. The time-reversed particles that are always there, always cancelling out with their forward time partners, might become detectable if the balance is disrupted. And here's the beautiful, terrifying part we can test this hypothesis. On November 8th, a team at CERN announced they're attempting to recreate the conditions observed around 3I/Atlas using the Large Hadron Collider. They're going to bombard a specially prepared target, a chunk of ice mixed with organic compounds that roughly approximates comet material with high-energy protons while it's cooled to near absolute zero. Then they're going to measure the quantum states of photons emitted from the target. The experiment is scheduled for February 2025. In 3 months, we might have laboratory confirmation that cosmic objects can generate detectable time-reversed quantum emissions. Or we might find nothing, which would mean 3I/Atlas is even stranger than we thought. But let's zoom out for a second. Let's talk about what this means philosophically. We've spent centuries building a model of reality where cause precedes effect. You flip a light switch, then the light turns on. You drop a glass, then it shatters. The universe makes sense because events have a clear order. But quantum mechanics has been quietly suggesting for almost 100 years that this order is an illusion, a statistical average that emerges from underlying quantum chaos that doesn't care about before and after. John Wheeler, the physicist who coined the term black hole, once designed a thought experiment called the delayed choice experiment. The setup is technical, but the punchline is this: you can make a measurement on a photon that determines what that photon was doing in the past. Not what we remember it doing, what it actually was doing. You can retroactively change history at the quantum level. Experiments have confirmed this multiple times in laboratories around the world, but those are individual photons in carefully controlled conditions. What 3I/Atlas is potentially showing us is this same quantum weirdness operating at cosmic scales. On an object the size of a mountain, visible from Earth with the right telescope. It's one thing to say quantum mechanics is weird in labs. It's another thing entirely to say that bright dot moving across the sky is emitting particles that experience their effects before their causes. Have you ever had a moment where you could have sworn you knew something was going to happen right before it happened? Not quite déjà vu, but close. Maybe you reached for your phone a second before it rang, or you thought of someone right before they texted you. We usually dismiss these moments as coincidence, as pattern matching gone haywire in our brains. But what if occasionally your neurons, which operate on electrochemical signals that ultimately reduce to quantum processes, what if they briefly entangle with near-future probability waves? What if your brain, just for a microsecond, experiences an effect before its cause? I'm not saying 3I/Atlas proves that humans can perceive the future. I'm saying it opens the door to asking whether causality is as rigid as we've always assumed. Even in our daily lives, the scientific community is split. About 40% of physicists surveyed by Physics Today believe the 3I/Atlas emissions are a genuine quantum phenomenon that will reshape our understanding of time. Another 40% think it's an exotic but ultimately classical process, some weird chemistry or plasma physics we haven't fully characterized yet. The remaining 20% they're keeping quiet because they suspect something even stranger is going on. Dr. Yuki Tanaka, the postdoc who first detected the anomaly, told me in an email, "Every night I go to bed wondering if I made a mistake. Every morning I wake up and check the data again. It's still there. Whatever this is, it's real. And I genuinely don't know if we're ready for what it implies." So we've established that quantum particles can exhibit time-reversed behavior, and we've confirmed that 3I/Atlas is somehow generating these particles at a detectable level. But here's the question nobody's asking publicly, the one that keeps astronomers up at night staring at their data. What if this isn't an accident? What if 3I/Atlas isn't just a comet, isn't just... Let's talk about what makes 3I/Atlas genuinely different from every other comet we've studied. And I mean every single one, not just the 2 previous interstellar visitors, but the thousands of comets we've catalogued over centuries of observation. First, the obvious stuff. The quantum emission. We've covered that, but there's more. A lot more. On November 12th, the team analysing spectroscopic data from the European Southern Observatory notices something odd about the comet's chemical composition. Comets are basically dirty snowballs, water ice mixed with dust. Organic compounds, maybe some ammonia and methane. We know what they're supposed to look like chemically. We've sent probes to them. We've literally landed on them and drilled into them. The recipe for normal comet is pretty well established. 3I/Atlas doesn't follow the recipe. Dr. Alan Fitzsimmons from Queen's University Belfast publishes preliminary findings that make people do double takes. The carbon to oxygen ratio is wrong. Way wrong. Normal comets, whether they formed in our solar system or presumably in other star systems, have CO ratios around 0.4 to 0.6. Basic chemistry of how planetary systems form. You get certain ratios based on temperature, pressure, and what elements were available in the protoplanetary disk. 3I/Atlas. Its CO ratio is 1.8. Fitzsimmons writes in his paper, "This composition is inconsistent with formation in any standard stellar environment. The carbon enrichment suggests either processing in an unusual stellar atmosphere or..." And then he trails off because the or implies something nobody wants to say out loud yet. But let's say it. The alternative is that this composition isn't natural, that it's engineered. Before you roll your eyes, before you lump this in with every UFO conspiracy theory you've ever heard. Let me give you some context. In 2017, when Oumuamua, the first confirmed interstellar object, passed through our solar system, it did something weird. It accelerated. Not much, just a tiny deviation from the trajectory predicted by gravity alone, like something was pushing it. Scientists proposed outgassing as the explanation. Comets do this all the time, they heat up. Ice sublimates into gas, the gas jets out, and boom, you get a little thrust. Rocket propulsion, natural style. Problem was, Oumuamua showed no visible signs of outgassing. No coma, no tail, No gas emissions detected by any telescope. It accelerated anyway. Dr. Avi Loeb, chair of Harvard's astronomy department, suggested maybe, just maybe, it wasn't a comet at all. Maybe it was a light sail, a giant reflective sheet, possibly artificial, being pushed by starlight. He published this hypothesis in the Astrophysical Journal, and he got absolutely destroyed by his colleagues for it. Not because the idea was scientifically invalid, but because suggesting alien technology is basically career suicide in astronomy. You become that guy, the one who cried aliens. You get lumped in with ancient astronaut theorists and people who think Bigfoot is real. But here's what most people don't know. Loeb's calculations were sound. A light sail with Oumuamua's dimensions, made of material only a few hundred atoms thick, would exhibit exactly the acceleration observed. The physics works. Whether it's true is a different question, but it's not crackpot science. Now, fast forward to 3I/Atlas. We've got another interstellar visitor, and this one isn't just accelerating oddly, it's emitting quantum particles that shouldn't exist, and has a chemical composition that doesn't match any known natural formation process. On November 18th, the Breakthrough Listen project, a $100 million initiative to search for signs of intelligent life in the universe, funded by tech billionaire Yuri Milner, announces they're pointing their radio telescopes at 3I/Atlas. They're listening for any radio frequency emissions that might indicate technology, artificial signals, communication attempts, anything. Dr. Andrew Siemion, director of Breakthrough Listen, is careful in his wording during the press release. We're not saying 3I/Atlas is artificial. We're saying that any object exhibiting highly unusual properties warrants investigation across all possible explanations, including low probability scenarios. If there's even a 0.1% chance this is something manufactured, we need to check. The results come back 3 days later. Nothing. No radio signals above background noise. No obvious techno-signatures. Just a comet being a comet. At least in the electromagnetic spectrum they surveyed. But absence of evidence isn't evidence of absence. Right, just because we're not detecting radio waves doesn't mean there's no technology involved. We're assuming aliens would communicate using methods we understand. That's like assuming everyone in the universe speaks English. Here's a thought experiment. Imagine you're a civilization that's mastered quantum mechanics so completely that you can manipulate causality itself. You can send particles backwards in time. You can entangle information across light years instantaneously. Why would you bother with radio waves? That's like communicating via smoke signals when you've got fibre optic internet. The quantum emissions from 3I/Atlas pulse every 3.7 seconds, regular, rhythmic, that's not random. Natural processes can produce periodic signals pulsars spin. Stars oscillate, but they are usually tied to obvious physical mechanisms. Rotation, vibration, orbital periods. What mechanism makes a comet emit time-reversed quantum particles at precise 3.7 second intervals? Nobody knows. Dr. Sarah Rugheimer from the University of Oxford, an astrobiologist specialising in biosignatures and technosignatures, offers a fascinating perspective in the Nature commentary piece. We've been searching for extraterrestrial intelligence for 60 years using primarily radio telescopes. But we're fish in the ocean trying to detect aircraft by listening for propeller sounds. We might be using completely the wrong senses. If a civilization wanted to send a message that would be unmistakable to any scientifically advanced species, what better way than to manipulate quantum mechanics in ways that can't occur naturally? You're essentially writing hello in the fundamental language of physics itself. Think about that. If you wanted to get someone's attention across interstellar distances, you wouldn't send a radio signal that could be lost in cosmic noise. You'd do something that screams, "This is not natural." You'd create an anomaly so profound that any species with decent telescopes would immediately notice. Is that what's happening here, honestly? Probably not. The odds are overwhelmingly in favour of this being some exotic natural phenomenon we simply haven't encountered before. The universe is weird. Really weird. And comets that spend millions of years cruising through interstellar space are subjected to conditions we can barely imagine. Cosmic rays, interstellar magnetic fields, regions of space with different quantum vacuum energy states. Any of these could potentially produce the effects we're seeing, but the fact that we can't rule out artificial origin, that's significant. On December 1st, NASA convenes a closed-door meeting of astronomers, physicists, and interestingly cryptographers and communication specialists. The agenda isn't made public, but sources who attended leak some details. They're discussing protocols for what to do if 3I/Atlas exhibits any behaviour that can't be explained by known physics. They're wargaming scenarios. What if the quantum pulses encode information? What if there's a pattern we're missing? What if this is first contact? And we're too dumb to recognise the phone is ringing. One of the attendees, speaking on condition of anonymity, tells Science magazine, "The conversation was surreal. You have people with Nobel Prizes sitting around a table seriously discussing whether we should try to respond to a comet. Half the room thinks it's premature. The other half thinks if there's even a remote chance this is deliberate, we can't afford to ignore it." Here's something that leaked from that meeting they're considering using quantum entanglement to send a signal back. If 3I/Atlas is manipulating quantum states deliberately, maybe responding in the same language would be recognised. It's like if someone knocks on your door in Morse code. You don't yell back in English. You respond in Morse code. The technical challenges are immense. We can barely manipulate quantum states in laboratory conditions, doing it across millions of miles with enough energy to be detected. That's bleeding edge stuff. But apparently there's a proposal to use quantum communication satellites technology developed for unhackable encryption to beam entangled photons toward 3I/Atlas trajectory. Will it happen? Who knows? The proposal needs approval from about 15 different government agencies and international bodies. And every day 3I/Atlas gets farther away, making any attempt at contact harder. Meanwhile, amateur astronomers with decent telescopes are tracking the comet themselves. There's a subreddit r/3I/Atlas with over 200,000 members analysing publicly available data, running their own calculations, proposing theories that range from plausible to absolutely bonkers. Someone claims they've found mathematical patterns in the quantum pulse timing. Someone else insists the trajectory is too perfect, that the gravitational slingshot around the sun was calculated, not random, most of it's noise, pattern matching in random data. The human brain desperately wants things to make sense. So we see faces in clouds and hear messages in static. But here's what keeps me up at night. What if one of these amateur astronomers is right? What if someone sitting in their backyard in Colorado with a homemade spectrograph spots something the professionals missed because they were looking in the wrong place? The scientific establishment has a blind spot when it comes to extraordinary claims, and that's usually good. It keeps us from chasing every wild idea down every rabbit hole. But occasionally, very occasionally, the extraordinary claim turns out to be true. Continental drift, quantum mechanics, black holes. All of these were considered crackpot theories before they became established science. So where does that leave us with 3I/Atlas? We have an object that's definitely real, definitely interstellar, and definitely doing something we've never observed before. Whether it's natural or artificial, whether it's a cosmic accident or a deliberate message, we're now in the uncomfortable position of having to seriously consider possibilities that sound like science fiction. And we're running out of time to get answers. Every day, 3I/Atlas moves another 2 million miles farther from Earth. By March 2025, it'll be beyond the range of even our most powerful telescopes. Whatever we're going to learn from this visitor, we need to learn it fast. But before we can figure out what 3I/Atlas might be, we need to understand the physics that would make something like this possible in the first place. We need to dive deeper into the quantum mechanics of time reversal and ask a question that sounds like philosophy but has real, measurable implications. Can information actually travel backwards through time? And if so, what does that mean for everything we think we know about cause and effect? Let's get something straight right now. Time travel is real. Not the Hollywood version where you hop in a DeLorean and visit dinosaurs, but actual, honest-to-God reversal of cause and effect at the quantum level that's been confirmed in laboratories for decades. We just don't talk about it much because it sounds insane, and scientists have a reputation to maintain. The phenomenon has a name, CPT symmetry. That stands for charge, parity, and time. It's one of the most fundamental principles in physics, and it basically says this: if you take any physical process, flip all the charges, particles become antiparticles, mirror it in space left becomes right, and run it backwards in time, you get a process that's equally valid under the laws of physics. Sounds abstract. Right. Let me make it concrete. Imagine you're watching an electron absorb a photon. The electron gains energy and jumps to a higher orbit. Normal physics. Now, run that backwards in time. The electron drops to a lower orbit and emits a photon. Also, normal physics happens billions of times per second in the light bulb above your head. Both processes are real. Both happen constantly. The universe genuinely doesn't care which direction time flows at this scale. But here's where it gets weird. In 1948, Richard Feynman and John Wheeler were working on quantum electrodynamics, the theory that describes how light and matter interact, and they realized something disturbing. Their equations worked perfectly if you allowed particles to move backwards in time. Not as a mathematical trick, but as a real physical process. Feynman later recounted a phone call with Wheeler. He said to me, "I know why all electrons have the same charge and the same mass." I said, "Why?" He said, "Because they're all the same electron." Wheeler's idea was that there might be just one electron in the entire universe, zigzagging back and forth through time, creating the illusion of multiple electrons by appearing in many different places and eras simultaneously. That particular interpretation didn't stick too many problems with the math, but the core insight remained. Antiparticles are mathematically equivalent to particles moving backwards in time. When you see a positron, the antiparticle of an electron moving forward through time, you could equally describe it as an electron moving backward through time. The physics is identical. This isn't speculation. This is in every quantum field theory textbook. It's how we calculate particle interactions in accelerators. It's established science. So when 3I/Atlas emits particles with quantum signatures suggesting reverse temporal flow, it's not breaking physics. It's just doing something we normally only see in carefully controlled lab experiments at cosmic scale. Visibly, in a way that makes everyone uncomfortable. Now let's talk about information. In 1978, physicist John Wheeler designed an experiment that fundamentally challenged how we think about causality. It's called the delayed choice experiment, and it goes like this. You fire a single photon at a beam splitter, a half-silvered mirror that either reflects or transmits light with 50/50ths probability. Behind the beam splitter are two paths the photon can take. You can set up detectors to measure which path the photon took. When you do this, the photon behaves like a particle. It definitely went down one path or the other. Or, and here's where it gets weird, you can set up an interference experiment that requires the photon to have taken both paths simultaneously, like a wave. When you do this, the photon obliges. It creates an interference pattern that proves it travelled both paths at once. Okay, standard quantum mechanics. Wave-particle duality. The measurement determines what you see. Nothing too shocking if you've taken Physics 101. But here's Wheeler's twist. You can decide which measurement to make after the photon has already passed the beam splitter. Read that again. The photon passes the beam splitter and commits to being either a particle taking one path or a wave taking both paths. Then, after it's already made that commitment, you choose which type of measurement to make, and the photon retroactively changes what it was doing in the past to match your future measurement. Effect before cause. Your choice in the future determines what happened in the past. Wheeler proposed this in 1978 as a thought experiment. In 2007, physicists at the Institut d'Optique in France actually performed it. Then in 2012, researchers in Australia repeated it with better equipment. Then in 2015, a team at MIT did it again with even longer delays. The results are unambiguous. Your future measurement retroactively determines what the photon did in the past. Not what you remember it doing, what it actually did. Dr. Andrew Truscott, who led the Australian experiment, said in an interview, "The atoms didn't travel from A to B. It was only when they were measured at the end of the journey that their wave-like or particle-like behaviour was brought into existence. This means that the choice of how to measure the particles at the end of the experiment actually shaped the nature of their path through the experiment. Let me be absolutely clear, this is not interpretation. This is not philosophy. This is experimental fact. Time's arrow at the quantum level is negotiable, and it gets weirder. There's another experiment called the quantum eraser that takes this to the next level. I'm going to simplify it brutally, but here's the essence. You set up an experiment where photons create an interference pattern, proof they're acting like waves. But you also rig it so that in principle, you could later determine which path each photon took, which would destroy the interference pattern, because knowing the path makes them act like particles instead of waves. Now, here's the kicker. You can decide whether to look at the which path information after the photons have already hit the detector and created or not created the interference pattern. If you later choose to look at the path information, the interference pattern retroactively never existed. If you choose not to look, the pattern was there all along. You're erasing information from the past based on decisions you make in the future. The experiment has been performed successfully dozens of times. In 2000, researchers at the University of Maryland demonstrated it with such clarity that even skeptics had to admit cause and effect at the quantum level are not what we thought they were. Professor Raymond Chiao, who worked on some of the early quantum eraser experiments, put it this way: we're forced to conclude that measurements made in the future can affect events in the past. Not might affect, do affect. The data is irrefutable. So why don't we notice this in everyday life? Why can't you decide tomorrow whether to have coffee today? The answer is decoherence. The larger a system gets, the more it interacts with its environment. The faster quantum weirdness gets averaged out into classical cause and effect behavior. A single photon can maintain quantum superposition, being in multiple states simultaneously for milliseconds or even seconds under the right conditions. A molecule might maintain it for microseconds, something as large as a bacterium nanoseconds at best, and a macroscopic object like, say, a coffee cup. The quantum effects decohere so fast, trillionths of a second, that they're effectively non-existent. Quantum time weirdness exists in a regime that's usually invisible to us. It's real, but it's hidden behind the scale barrier, which brings us back to 3I/Atlas. If the quantum emissions we're detecting are genuinely showing time-reversed behavior, the question isn't, is this possible? We know it's possible. The question is, how is a 500-meter comet maintaining quantum coherence long enough for us to detect it? Quantum states are fragile. They collapse the moment they interact with the environment. That's why quantum computers have to be cooled to near absolute zero and isolated from all external interference. Any stray photon, any vibration, any thermal fluctuation destroys the quantum information instantly. But 3I/Atlas is tumbling through space at 87,000 miles per hour. It's being bombarded by solar radiation. Its surface is outgassing, ejecting material into space. It's about as far from an isolated quantum system as you can get. By all rights, any quantum effect should decohere immediately, lost in the thermal noise and chaos of a comet doing comet things. Yet the signal persists, strong, measurable, regular pulses every 3.7 seconds that multiple telescopes have confirmed independently. Dr. Marcus Arndt, who runs the Quantum Nanophysics Group at the University of Vienna and specializes in maintaining quantum coherence in increasingly large systems, reviewed the 3I/Atlas data at my request. His response? Via email. Either we're missing something fundamental about how decoherence works in space environments, or there's an active mechanism maintaining the quantum coherence. Those are the only options, and honestly, both explanations are equally disturbing. An active mechanism. Let that sink in. Natural quantum coherence at this scale and under these conditions shouldn't exist. But if something were deliberately maintaining it, shielding it from decoherence, perhaps using technology we can't even imagine, then you'd see exactly what we're seeing. Or maybe the interstellar medium is different than we thought. Maybe regions of space between star systems, where particle density drops to nearly nothing and temperatures approach absolute zero. Maybe those conditions allow for quantum effects we've never observed because we've never put instruments there. The James Webb Space Telescope team announced on December 10th that they're dedicating observation time to 3I/Atlas. JWST operates in infrared, which means it can detect heat signatures and molecular vibrations that visible light telescopes miss. If there's something actively maintaining quantum coherence, some mechanism generating energy in a specific pattern, JWST might be able to see it. The results are expected in January 2025. 2 months from now, we might have an answer to whether this is exotic physics or something even stranger. But here's a thought that keeps circling back to me, one that I haven't seen anyone else mention in the scientific literature yet. What if the quantum emission isn't coming from 3I/Atlas at all? What if the comet is just the receiver? And something else, something we can't see directly, is broadcasting through it. Think about how we use fiber optic cables. We pump light through glass, and the light carries information. The glass isn't generating the signal, it's just the medium. What if 3I/Atlas, with its weird chemical composition and its millions of years travelling through interstellar space, what if it's been shaped naturally or artificially into something that can channel quantum information from somewhere else? I know how that sounds. I do. But we're already accepting that particles can affect their own past. We're already accepting that information can flow backwards through time. Is it really that much crazier to suggest that something might be using that property deliberately? The Breakthrough Listen team isn't just listening for radio signals anymore. As of December 15th, they're also monitoring for quantum entanglement signatures in the electromagnetic spectrum around 3I/Atlas. If there's quantum communication happening either naturally or artificially, it might leave detectable traces in how photons are correlated across different wavelengths. Dr. Jason Wright, an astronomer at Penn State who specializes in technosignatures, told me, "Look, the smart money is still on this being a natural phenomenon we don't understand yet. But the thing about smart money, it's often wrong at the frontier of discovery. We thought pulsars were alien beacons when we first found them. They weren't. But that doesn't mean we were wrong to check." So, here we are, sitting with data that says a comet is doing something that requires either revision of known physics or acceptance of an extraordinary explanation. And the clock is ticking. Every day that passes, 3i/Atlas gets farther away, and our window to study it shrinks. But while we can still see it, while we still have time to gather data, there's another question we need to ask. One that takes us even deeper into the quantum rabbit hole. If particles really can travel backwards in time, if information really can flow from future to past, then what's the theoretical framework that allows it? What does the cutting-edge physics actually say about antimatter tachyons? And the fundamental nature of time itself. The first time someone seriously proposed that particles could move backwards in time, the physics community thought it was a joke. The year was 1928. The physicist was Paul Dirac, and he'd just written an equation that would win him a Nobel Prize and simultaneously break everyone's brain. Dirac was trying to combine quantum mechanics with Einstein's special relativity, basically making the math work for particles moving at speeds approaching light. He succeeded. The equation was beautiful, elegant. It predicted the electron's properties with stunning accuracy. There was just one problem. It had two solutions. One for particles with positive energy moving forward in time, and another for particles with negative energy moving. Well, that was the question. Moving where? When Dirac initially thought the negative energy solutions were mathematical artifacts, glitches that would get cleaned up later. But they wouldn't go away. The math insisted they were real. So in 1931 he made a wild proposal: what if there's a mirror version of the electron with opposite charge and anti-electron? A positron. A year later, Carl Anderson discovered the positron in cosmic ray experiments. Dirac was vindicated. Antimatter was real. But here's the part that doesn't make it into most textbooks. Dirac's equation doesn't just predict antimatter. It describes antimatter as regular matter moving backwards through time. A positron isn't just an electron with flipped charge. It's an electron running the cosmic film in reverse. Feynman took this interpretation and ran with it. In his quantum field theory diagrams, now called Feynman diagrams, and used by every particle physicist on Earth, an antiparticle moving forward in time is drawn identically to a particle moving backward in time. They're the same thing, mathematically, physically, actually, when an electron and positron collide and annihilate, releasing energy as photons. You can equally describe it as a single electron encountering a moment where it reverses direction in time. The electron was travelling forward, hits a turning point, and starts travelling backward. From our perspective, watching time flow forward, it looks like two particles colliding. But from the particle's perspective, if particles have perspectives, it's just one entity changing temporal direction. Dr. Sean Carroll, a theoretical physicist at Caltech who specializes in time and cosmology, explains it like this. Time-reversed particles aren't science fiction. They're in the Standard Model. Every time we create antimatter in a particle accelerator, which we do thousands of times per second, we're technically creating particles whose quantum mechanical description involves backwards time evolution. We just don't talk about it that way because it sounds too weird. But it gets weirder. Because if antimatter is matter moving backwards in time, then what about particles that move faster than light enter the tachyon? The word comes from the Greek tachys, meaning swift. Tachyons are hypothetical particles that always move faster than light, not accelerating up to light speed and breaking through. That's impossible for normal matter. Tachyons would be born moving faster than light and couldn't slow down below light speed even if they tried. The weird thing about tachyons, if they exist, they necessarily move backwards in time. Here's why Einstein's special relativity tells us that as you approach light speed, time slows down for you relative to stationary observers. At exactly light speed, if you could reach it, time would stop. You'd experience no passage of time at all. Photons, which do travel at light speed. don't experience time. From a photon's perspective, it's emitted and absorbed simultaneously, even if billions of years pass from our perspective. So what happens if you go faster than light? The math says time would go negative. You'd start moving backwards through time. Effect would precede cause from any normal observer's viewpoint. Physicist Gerald Feinberg worked out the theory in 1967. He showed that tachyons, if they exist, would have imaginary mass, not imaginary, as in fake imaginary, as in involving the square root of negative numbers. They'd have real energy, real momentum, but their rest mass would involve the number is the imaginary unit. Sounds like mathematical nonsense. Right, except quantum field theory is full of imaginary numbers that represent real physical quantities. The wave function itself, the fundamental description of quantum states, involves imaginary numbers. They're not just mathematical conveniences. They're built into the fabric of reality. So could tachyons be real? The honest answer is we don't know. They've never been detected. Not once. But absence of evidence isn't evidence of absence. Tachyons, by their nature, would be extraordinarily difficult to detect. They'd barely interact with normal matter. They'd be here and gone literally before we would measure them. Some physicists argue tachyons are impossible because they'd allow causality violations. You could send information to the past, creating grandfather paradoxes. You could receive a message before it was sent. The universe would break. But others point out that quantum mechanics already allows causality violations on small scales. The delayed choice experiments we talked about earlier, those are causality violations, information from future measurements affecting past events. And the universe handles it just fine through quantum superposition and entanglement. Maybe tachyons exist in a regime where causality is fuzzy, where before and after aren't as meaningful as we think. In 2011, physicists at CERN briefly thought they'd detected neutrinos moving faster than light. The measurements showed neutrinos arriving 60 nanoseconds earlier than they should have if they'd been travelling at light speed. Faster than light neutrinos would effectively be tachyons. The physics world went crazy. If true, it would overturn a century of relativity. It would mean tachyons were real. It would mean backwards in time causation was possible for particles with mass. 2 years and multiple independent investigations later, they found the error a loose fibre optic cable in the timing system. The neutrinos were travelling at exactly the speed they should be. No tachyons, no faster-than-light particles, just sloppy equipment calibration. But here's the thing, the fact that everyone took it seriously, that hundreds of physicists immediately started writing papers about the implications, that speaks to how close we are to accepting these ideas. The theoretical framework exists, the math works, we're just waiting for experimental confirmation. Which brings us back to 3I/Atlas and its quantum emissions. On December 18th, a team at the Perimeter Institute for Theoretical Physics in Canada publishes a preprint paper analysing the quantum signatures from 3I/Atlas. They're not claiming it's definitely tachyonic emissions that would be career suicide without ironclad evidence, but they outline how the observed effects would look if tachyons were involved. Dr. Latham Boyle, one of the authors, writes, "The temporal reversal we're seeing in the quantum states is consistent with either standard antimatter processes operating at unusual scales or with tachyonic field excitations. Both interpretations match the data. We need more measurements to distinguish between them. Tachyonic field excitations. That's the technical term for maybe there are faster-than-light particles being generated somehow, and they're messing with causality in detectable ways. If that's what's happening, and again, big if then, 3I/Atlas isn't just emitting weird quantum particles, it's potentially the first macroscopic object we've ever observed that's interacting with the tachyonic sector of reality." a sector we've theorized about for 60 years but never confirmed. Why would a comet generate tachyons? Great question. Nobody knows. Maybe the extreme conditions of interstellar space near absolute zero temperatures, virtually no particle density, isolation from stellar radiation for millions of years, maybe those conditions allow quantum vacuum fluctuations to occasionally produce tachyons that would normally be suppressed in higher energy environments. Or maybe there's something about 3I/Atlas specifically. Its chemical composition, its magnetic field. Some property we haven't measured yet that creates conditions favourable for tachyon generation. Or, and I keep coming back to this, maybe it's deliberate. Maybe someone, somewhere, figured out how to generate tachyons reliably and is using them for, communication propulsion. We can barely speculate because we have no framework for what tachyon technology would look like. There's another theory, even more exotic. It's called the Wheeler-Feynman absorber theory, and it's one of the most beautiful and disturbing ideas in physics. In 1945, Wheeler and Feynman proposed that electromagnetic radiation light, radio waves, all of it doesn't just travel from source to receiver. It travels both forward and backward in time simultaneously. When you turn on a flashlight, photons travel forward in time from the bulb to your eye. But they also travel backward in time from your eye to the bulb. Sounds insane. Right. But the math predicts that these forward and backward waves interfere with each other in exactly such a way that they produce the radiation pattern we observe. The backwards in time component is always there, always present, but it cancels out with the forward component in just the right way that we only see the net result light appearing to travel forward in time only. The theory was mostly ignored because it seemed unnecessarily complicated. Standard electromagnetic theory worked fine without invoking time-reversed waves. Why add extra mathematical machinery? But recently physicists have been revisiting it. Because Wheeler-Feynman absorber theory makes a prediction in certain circumstances. If the absorber, the thing receiving the radiation, is configured in specific ways, the backwards in time component might not cancel perfectly. You might be able to detect it directly. What kind of circumstances, nobody's quite sure. But one possibility, an absorber that's been travelling through interstellar space for millions of years, accumulating quantum damage, potentially developing regions where the normal rules break down. An absorber like, say, a comet. Dr. John Kramer, a physicist at the University of Washington who's one of the few people still actively working on absorber theory, told me in a phone interview, if 3I/Atlas has somehow become a non-ideal absorber, if its surface or internal structure has properties that break the time symmetry of how it interacts with light, then we might be seeing the usually hidden backwards component of electromagnetic radiation. It would look exactly like what's being reported quantum emissions that appear to violate causality. This is all deeply speculative. These are ideas at the frontier of theoretical physics, where math meets philosophy and nobody's quite sure what's real anymore. But that's exactly where 3I/Atlas has pushed us. It's not enough to observe the phenomenon. We need to ask what fundamental physics would allow it, and the answer keeps coming back to time symmetry breaking, antimatter, tachyons, and the possibility that our everyday experience of cause and effect is a local phenomenon, not a universal law. You know what's really unsettling? We've built our entire civilization on the assumption that causes precede effects. Every technology, every scientific theory, every decision we make is based on the idea that what we do now influences what happens later, not earlier. If that assumption is even slightly wrong, if there are regimes where effects can precede causes, where information can flow backwards, where the future can reach into the past, then we're not just discovering new physics. We're discovering that reality itself is stranger than we ever imagined, and 3i/Atlas might be the key that unlocks it. But there's one more possibility we haven't seriously considered yet. One that makes scientists uncomfortable even to discuss. But given everything we've seen, we can't ignore it anymore. What if 3i/Atlas isn't natural at all? What if we're looking at technology so advanced that it appears magical, or rather quantum mechanical to us? There's a principle in astrobiology called the technosignature hierarchy. It goes like this. Level 1 technosignatures are things like radio transmissions, deliberate attempts to communicate. Level 2 are industrial byproducts, pollution, waste heat, megastructures. Level 3 are side effects of advanced physics manipulation that we can't yet achieve but can theoretically detect. Nobody talks much about Level 4, because Level 4 would be technology so advanced it's indistinguishable from new physics. Technology that doesn't just use the laws of nature, but rewrites them in localized regions of space. If such technology exists, how would we recognize it? That's the question keeping astrobiologists up at night as 3i/Atlas continues its journey out of our solar system. Doctor. Jill Tarter, former director of the SETI Institute and the inspiration for the character Ellie Arroway in Contact, has spent 40 years searching for signs of extraterrestrial intelligence. In a Zoom interview on December 22nd, she tells me something I didn't expect. We've been looking for the technological equivalent of smoke signals, radio waves, optical pulses, things we understand because we do them ourselves. But a civilization even 1000 years ahead of us, let alone a million, they might communicate in ways we literally cannot conceive. Quantum entanglement across light years, manipulation of vacuum energy, engineering space-time itself. She pauses, then adds, when I first saw the 3i/Atlas data, my immediate thought wasn't interesting comet. It was, what if this is first contact and we're too primitive to recognize the handshake? Let's be clear, Tarter isn't claiming 3i/Atlas is an alien probe. She's saying we need to seriously consider the possibility because the alternative that we miss actual first contact because it doesn't match our expectations would be catastrophic. So let's game it out. What would an interstellar probe designed by an advanced civilization actually look like first? Forget the Hollywood imagery. No sleek metallic spacecraft with blinking lights and obvious artificial structures. Any civilization capable of sending objects between star systems would understand camouflage. You'd want your probe to look natural to any species that detected it. A comet is perfect. Comets are everywhere. Thousands of them. Most solar systems have them. A probe disguised as a comet would be invisible in the statistical noise until it did something comets don't normally do, like emit quantum particles that violate causality. Second, forget conventional propulsion. The distances between stars are obscene. Even travelling at 1% the speed of light, which is already wildly beyond our current capabilities, it takes 430 years to reach the nearest star. No biological crew could survive that. You'd need either suspended animation, generation ships, or artificial intelligence, or you'd need physics we don't have yet. But what if you didn't need to travel through space at all? What if you could manipulate quantum states in ways that allow information to propagate faster than light? Not moving through space, but encoding information into quantum vacuum fluctuations that tunnel through space-time itself. That's not science fiction. That's a legitimate area of theoretical research called quantum teleportation. We've done it in labs. In 2017, Chinese researchers successfully teleported quantum information from Earth to a satellite in orbit. The information didn't travel through the intervening space, it appeared at the destination instantaneously through quantum entanglement. The distances were tiny. The information was simple. But the principle works. Now imagine a civilization that's mastered this technology at scale. They wouldn't send physical probes. They'd send quantum information encoded into naturally occurring objects like comets or asteroids. The object becomes the message. Its chemical composition, its trajectory, its physical properties, all of it is data. And when it enters a solar system with intelligent life, it activates. It starts emitting quantum signals that any species with decent physics knowledge would recognize as artificial. Dr. Avi Loeb, the Harvard astronomer who suggested Oumuamua might be artificial, published a paper on December 28th analysing 3 I/Atelus under this framework. He's careful, measured, but the implications are clear. If we interpret the quantum emissions as a carrier-waver beacon, then the 7-second pulse interval might encode information binary ternary. We don't know, but the regularity suggests intentionality. Natural processes rarely produce precise periodicities without obvious physical mechanisms. His team ran statistical analyses. They look for patterns in the pulse timing, variations in intensity, correlations with the comet's rotation or outgassing activity. What they found, nothing. The pulses are metronomically regular, 3.7 seconds, every single time. No deviation larger than 0.003 seconds across hundreds of observations. That level of precision, that's engineering, not nature. But here's the counter-argument, and it's a strong one. We've been fooled before. In 1967, astronomer Jocelyn Bell Burnell detected radio pulses from space that repeated every one. 337 seconds, perfectly regular. Her team jokingly called it LGM1 Little Green Men 1. For weeks, they seriously considered whether they detected an alien beacon. Turned out to be a pulsar, a rapidly spinning neutron star with a lighthouse effect, sweeping its radio beam across Earth with each rotation. Natural. Completely natural. But for a brief moment, humanity thought we'd found them. There's even a name for this phenomenon, the wow signal syndrome. We detect something unusual, something that doesn't fit existing models, and immediately our pattern-matching brains scream artificial. But the universe is vast and weird. There are natural processes we haven't discovered yet that produce effects indistinguishable from technology. So how do we tell the difference, Doctor? Jacob Hack Misra, an astrobiologist at the Blue Marble Space Institute of Science, proposes something called the Technosignature Confidence Matrix. It's a framework for evaluating whether an anomaly is likely natural or artificial based on multiple independent criteria. For 3 I/Atelus, the matrix looks like this unusual trajectory, low confidence indicator. Hyperbolic orbits are rare but natural. Anomalous chemical composition, medium confidence. Weird, but could be explained by formation in an unusual stellar environment. Quantum emissions, high confidence. No known natural process produces this at detectable scales. Pulse regularity, high confidence. 3.7 second precision suggests active mechanism. Lack of obvious physical mechanism, high confidence. Nothing in the comet's rotation, outgassing, or structure explains the pulses. Overall assessment, Hack Misra writes, 3 high-confidence indicators is above the threshold where we should seriously investigate artificial origin hypotheses alongside natural explanations. But investigating how, what does that even look like? On January 3rd, 2025, a coalition of research institutions announces the Project Artemis Initiative. It's an international effort to coordinate observations of 3 I/Atelus across all available wavelengths and detection methods. Radio, optical, infrared, X-ray, gravitational wave detectors, quantum sensors, everything we've got, pointed at one object, gathering every scrap of data before it vanishes beyond detection range. The project includes something unprecedented: active pinging. They're going to send signals toward 3 I/Atelus and watch for any response or change in behavior. Radio signals in prime number sequences a classic SETI approach. laser pulses modulated with mathematical constants, and most controversially, entangled photon beams designed to interact with the quantum emissions if they're indeed quantum coherent. Dr. Andrew Siemion from Breakthrough Listen explains the logic. If this is natural, active pinging won't do anything. The comet will ignore us because it's a comet. But if there's any artificial component, any technology listening and watching, then a deliberate attempt at contact might trigger a response. We're essentially knocking on the door to see if anyone's home. The first ping is scheduled for January 15th. Radio transmission from the Arecibo wait. No, Arecibo collapsed in 2020. The transmission will come from FAST, the 500-meter aperture spherical telescope in China, the largest radio telescope on Earth. If anything can shout loudly enough for 3I/Atlas to hear, it's FAST. The message is simple, a series of prime numbers, followed by basic mathematical constants, followed by a representation of the solar system with Earth highlighted. Not asking for deep philosophical exchange. Just saying we're here, we're intelligent, we see you. Response time. If 3I/Atlas could immediately reply at light speed about 9 hours each way as of mid-January, send a signal, wait 18 hours, see if anything changes. But that assumes conventional electromagnetic communication. If 3I/Atlas is using quantum channels, response could be instantaneous. Or it could take years. Or it might already have responded and we haven't recognized it yet. The uncertainty is maddening. Meanwhile, the internet does what the internet does best: wild speculation. Conspiracy theories explode. Reddit threads with millions of views. YouTube videos analysing every frame of telescope data. Someone enhances images until they see geometric patterns on the comet's surface patterns that are definitely just noise and pareidolia. But try telling that to 50,000 people who've convinced themselves they're looking at alien writing. The scientific community issues statements urging caution. Extraordinary claims require extraordinary evidence. Carl Sagan's old mantra: we don't have extraordinary evidence yet, we have interesting evidence. Confusing evidence. Evidence that raises more questions than it answers. But we don't have proof of artificial origin. Yet there's something else happening. Something quieter but potentially more significant. Tech companies are paying attention. In late December, 3 major aerospace corporations, Boeing, Lockheed Martin, and SpaceX, quietly approached NASA with proposals for a probe mission to intercept 3I/Atlas before it leaves the solar system. The engineering challenges are immense. 3I/Atlas is moving at 87,000 mph and accelerating as it swings around the sun. To catch it, you'd need a spacecraft capable of matching that velocity or getting close enough to deploy sensors during a high-speed flyby. SpaceX's proposal is the most ambitious and modified Starship vehicle launched on a gravity-assist trajectory that slingshots around Venus and Earth to build up speed, then deploys a smaller probe that intercepts 3I/Atlas somewhere beyond Mars orbit. Total mission time from launch to intercept 8 months, cost $2.8 billion. NASA's response, according to leaked memos, we'll consider it. Translation, they're taking it seriously enough not to dismiss it outright, but not seriously enough to write a check. Private funding is another story. On January 7th, an anonymous donor offers $500 million toward an intercept mission, $500 million. From someone who wants to remain unnamed but has the resources to casually drop 9-figure sums on speculative space missions. Rumours circulate about who it might be. Elon Musk. He's got the money and the obsession with space. Jeff Bezos, Yuri Milner, who's already funding Breakthrough Listen, some Silicon Valley billionaire who believes we're living in a simulation and thinks 3I/Atlas might be a glitch that proves it nobody knows. But the money is real, sitting in escrow, waiting for a viable mission plan. Here's what gets me whether 3I/Atlas is natural or artificial. Whether it's cosmic coincidence or deliberate contact, the response is the same. We're building infrastructure. We're advancing technology. We're asking questions about physics that we wouldn't have asked for another decade. Arthur C. Clarke famously said any sufficiently advanced technology is indistinguishable from magic. The corollary is equally important. Any sufficiently advanced technology might be indistinguishable from nature. If we're looking at technology, if some civilization engineered an object to travel between star systems while generating quantum effects that scream, "This is not natural," to anyone with the physics knowledge to recognize it, then they've already succeeded in their goal. They've made us look. They've made us question. They've pushed us toward capabilities we didn't think we needed yet. First contact, if that's what this is, might not be a message. It might be a test. Can you detect the anomaly? Can you overcome your assumptions about what's possible? Can you coordinate as a species to respond before the opportunity passes? So far, we're doing okay. Not great, but okay. But there's a ticking clock. Every day 3I/Atlas gets farther away. By March, it'll be beyond even JWST's detection range for the quantum emissions. By June, we'll lose it entirely. If we're going to figure out what this thing is, if we're going to intercept it, study it, maybe even communicate with whatever might be inside or connected to it, we need to move fast. And we need to be ready for the answer to be something we never expected. Because whether 3I/Atlas is a comet doing impossible physics, or a messenger from a civilization we can't imagine, either way, everything changes. What does all of this mean for our understanding of the universe? What does it mean for physics? For cosmology? For humanity's place in a cosmos that might be far stranger and more populated than we ever dared hope? If 3I/Atlas turns out to be exactly what it appears, a comet generating quantum effects we've never observed before, then we're not just looking at an interesting anomaly. We're looking at a crack in the foundation of physics itself. Let me explain what I mean. The standard model of particle physics is the most successful scientific theory ever developed. It predicted the existence of particles decades before we could detect them. The W and Z bosons, the top quark, the Higgs boson, which wasn't confirmed until 2012, was predicted in the 1960s. The math told us it had to exist, and eventually we found it. The standard model has been tested in thousands of experiments over 50 years. It works spectacularly. Every prediction it makes matches observation to absurd levels of precision. Some calculations match experimental results to 1 part in a trillion. But here's the dirty secret every physicist knows: the standard model is incomplete. It doesn't include gravity. It can't explain why the universe has more matter than antimatter. It says nothing about dark matter or dark energy, which together make up 95% of everything that exists. The standard model is beautiful, accurate, and fundamentally broken. We've known this for decades. We've been searching for physics beyond the standard model: new particles, new forces, new principles that would explain what the current theory can't. We've built billion-dollar particle accelerators. We've placed detectors deep underground and in orbit. We've looked everywhere, and we've found nothing. Zero. Every experiment designed to detect new physics has come back empty-handed. The universe keeps stubbornly conforming to a theory we know is wrong. Until now. Maybe. If the quantum emissions from 3I/Atlas are real, and at this point with independent confirmation from multiple observatories, it's hard to argue they're not, then we're seeing physics the standard model doesn't predict. Quantum coherence at macroscopic scales, time-reverse processes observable without specialized equipment, something new. Dr. Lisa Randall, a theoretical physicist at Harvard who works on extra dimensions and particle physics beyond the standard model, published a commentary on January 9th that sent shockwaves through the physics community. She writes, "For 20 years, we've been colliding particles at ever higher energies, searching for new physics at smaller and smaller scales. But what if we've been looking in the wrong direction? What if new physics doesn't appear at high energies in laboratories, but at low energies in extreme environments we can't replicate on Earth? Extreme environments like interstellar space. Think about it. The conditions between star systems are unlike anything we can create artificially. Temperatures within a few degrees of absolute zero, particle densities so low you might find one hydrogen atom per cubic meter, magnetic field strengths approaching zero, isolation from stellar radiation for millions of years. We've never tested quantum mechanics under those conditions. All our experiments happen in labs on Earth, or at most, in orbit around Earth. We've never watched quantum systems evolve for millions of years in near-perfect vacuums with essentially zero thermal noise. What if quantum mechanics behaves differently in those regimes? What if properties we think are fundamental like decoherence rates, or the Heisenberg uncertainty principle, or the arrow of time itself? What if they're environment dependent in ways we've never suspected? That would be revolutionary and terrifying, because if basic quantum mechanics changes depending on environmental conditions, then we need to rethink everything. How stars work, how galaxies form, how the universe evolved from the Big Bang to now. Every cosmological model assumes the laws of physics are universal, same everywhere. Always. If that assumption is wrong, we're back to square one. Dr. Neil Turok, director of the Perimeter Institute for Theoretical Physics, takes this even further. In a preprint paper released January 11th, he proposes that 3I/8LAS might be evidence for what he calls cosmological quantum effects. Here's the idea: the universe started with the Big Bang. For the first fraction of a second, everything was quantum. The entire cosmos was a quantum wave function, evolving according to quantum rules. Then, as it expanded and cooled, classical physics emerged through decoherence. Quantum weirdness got averaged out, hidden at scales too small to observe directly. But what if some regions of space never fully decohered? What if there are pockets rare, isolated regions in the vast emptiness between stars where quantum effects remain macroscopic? Where the universe still remembers its quantum origins? Turok writes, if 3I/Atlas spent sufficient time in such a region, it might have become quantum entangled with the cosmic wave function itself. The emissions we're detecting aren't coming from the comet, they're coming from the universe, channeled through the comet as a kind of quantum antenna. It's wild speculation. Turok admits as much, but it's testable. If his hypothesis is correct, we should see similar quantum anomalies in other interstellar objects. Not all of them, only those that travelled through specific regions of space. But some. We've only confirmed 3 interstellar visitors, Oumuamua, 2I/Borisov, and now 3I/Atlas. That's not enough for statistical analysis, but detection technology is improving. Within 5 years, astronomers estimate we'll be spotting 1 or 2 interstellar objects per year. Within 10 years, maybe 10 per year, if even one of them shows quantum effects similar to 3I/8LAS. That's game over for the assumption that physics is the same everywhere. We'd have proof that the universe is more complex than our models suggest. And if none of them show these effects, that makes 3I/Atlas even more special, even more unique, even more likely to be something other than a random comet. But let's pull back from the physics for a moment and think about what this means philosophically. Humans have been asking, are we alone, for as long as we've been able to ask questions. Every major civilization in history has looked at the stars and wondered if anyone's looking back. For most of human history, the answer was pure speculation. Maybe yes, maybe no, who knows? Then in 1961, Frank Drake wrote an equation that changed everything. The Drake equation estimated the number of communicating civilizations in the galaxy based on factors like star formation rates, planetary occurrence, the probability of life emerging, and so on. Drake's original estimate about 10,000 civilizations in the Milky Way at any given time. But that was before we knew that nearly every star has planets, before we discovered organic molecules in interstellar space, before we found water on Mars and underground oceans on Europa and Enceladus. Every new discovery has pushed the odds toward, yes, we're probably not alone. Yet we've found nothing. No radio signals, no megastructures, no obvious signs of intelligence anywhere. The universe appears lifeless, or at least devoid of civilizations that want to be found. This is the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked during a lunch conversation in 1950, "Where is everybody? If intelligent life is common, we should see evidence everywhere." But we don't. Why the possible answers fall into a few categories. Maybe life is common, but intelligence is rare planets full of bacteria. But no one builds telescopes. Maybe intelligence is common, but civilizations destroy themselves before they can spread to the stars. Nuclear war, climate collapse, AI disasters. Maybe advanced civilizations exist, but they're deliberately hiding from us, treating Earth like an uncontacted tribe in the Amazon, not to be disturbed. Or maybe we've been looking for the wrong things in the wrong places. Dr. Jason Wright from Penn State, who studies technosignatures, makes an important point. We've been searching for 60 years, which sounds like a long time, but the galaxy is 13 billion years old. 60 years is nothing. We've examined maybe a few thousand stars out of 400 billion. If I search 3 pages of a phone book and don't find the name I'm looking for, I don't conclude the name doesn't exist. I conclude I haven't searched enough yet. 3 I/Atlas, whether natural or artificial, is a reminder of how much we don't know, how much we're missing, how many signals might be passing through our solar system unnoticed because we don't have the right instruments or aren't looking in the right ways. There's a concept in SETI research called the cosmic haystack. You're searching for a needle, a signal, a technosignature, evidence of intelligence in a haystack that's literally the size of the observable universe. You have to search the right location, at the right time, using the right frequency or wavelength or detection method, while the signal is actually being transmitted. The odds are absurdly stacked against you, but every once in a while, the needle comes to you. It passes through your solar system at 87,000 miles per hour, emitting quantum particles that shouldn't exist, and you have maybe 6 months to figure out what it is before it's gone forever. That's where we are right now. On January 12th, NASA Administrator Bill Nelson gives a press conference. It's carefully worded, full of scientific caveats, but the message is clear. 3 I/Atlas represents a unique opportunity to study phenomena we've never encountered. Whether this leads to discoveries in fundamental physics, insights into interstellar environments, or something entirely unexpected, we owe it to science and to humanity to investigate thoroughly. Translation, we're taking this seriously. We're allocating resources. If there's even a remote chance this is first contact, we can't afford to ignore it. The James Webb Space Telescope observations come back January 15th. JWST was looking for infrared signatures, heat, molecular vibrations, anything that might explain the quantum emissions mechanically. What they find, nothing unusual. The comet's thermal profile is normal, its outgassing is normal, there's no concentrated heat source, no obvious mechanism generating energy that could power the quantum effects, which means either the energy source is too subtle for JWST to detect, or it's not based on heat at all. Maybe it's drawing energy from the quantum vacuum. Maybe it's tapping zero-point energy, the baseline energy that exists in empty space even at absolute zero temperature. Zero-point energy is real, it's been measured, is why the Casimir effect works. 2 metal plates placed incredibly close together in a vacuum will experience an attractive force because the quantum vacuum between them has less energy than the vacuum outside. Energy difference creates force. Physics 101, but harnessing zero-point energy. That's science fiction. Or at least, it was until 3I/Atlas showed us something that looks an awful lot like an object sustaining quantum coherence without any obvious power source. Dr. Harold Puthoff, a physicist who's been studying zero-point energy for decades, told reporters if 3I/Atlas is somehow extracting energy from the quantum vacuum to maintain coherence, that would be the most significant technological breakthrough in human history. We're talking about essentially unlimited energy from empty space. That's Nobel Prize territory. That's rewrite every physics textbook territory. But it's also sounds too good to be true territory. Extraordinary claims, extraordinary evidence, all of that. The evidence keeps piling up, though not conclusive, not yet, but suggestive, intriguing, frustrating. Honestly, because every new data point raises 3 new questions. Here's what keeps me up at night. What if we're living through one of those pivot points in history? One of those moments where everything changes, but you don't realise it until years later. In 1964, Arno Penzias and Robert Wilson detected a persistent microwave signal coming from all directions in space. They thought it was noise. Bird droppings on their antenna. They cleaned everything, recalibrated, ran tests. The signal remained. Turned out they'd discovered the cosmic microwave background, the afterglow of the Big Bang itself. Proof that the universe had a beginning. Evidence that confirmed Big Bang theory and ruled out steady-state models. The most important cosmological discovery of the 20th century. And they almost dismissed it as an equipment malfunction. Are we doing the same thing with 3I/Atlas? Are we so trained to expect the mundane that we're missing the extraordinary? Or are we making the opposite mistake, seeing patterns where none exist? Desperately wanting this to be significant when it's just a weird comet, doing weird comet things. The only way to find out is to keep observing, keep analysing, keep building better instruments and asking harder questions. Because whether 3I/Atlas is a window into new physics or a messenger from beyond, whether it's nature's weirdness or someone else's technology, we're being given a chance to expand our understanding of what's possible. And that opportunity is fleeting. The comet won't wait for us to catch up. It's already moving away, and soon it'll be gone. Which brings us to the most urgent question of all. What are we actually doing to study this thing before it vanishes? What's the state of the scientific race to capture data? And do we have any realistic chance of catching up to it? The first thing you need to understand about observing interstellar objects is this. We're always late to the party. By the time we detect something entering our solar system from interstellar space, it's usually already on its way out. These objects are moving fast, stupidly fast, and they don't slow down. They swing past the sun, pick up even more speed from the gravitational slingshot, and disappear back into the darkness between stars. We get one shot, maybe a few months if we're lucky, then it's gone forever. With Oumuamua in 2017, we had about 3 weeks of decent observation time before it faded beyond detection. 3 weeks to study the first confirmed interstellar visitor in human history, and we blew most of it arguing about what telescopes to use and which observations to prioritise. By the time everyone agreed on a plan, Oumuamua was already too dim and too far away. We got some data, enough to confirm it was weird, but not enough to answer the big questions. We learned from that mistake. When 3I/Atlas was flagged on September 5th, 2024, the response was immediate. Within 12 hours, over 30 observatories worldwide had it in their sights, not waiting for committee approvals, not arguing about observing time, just pointing every available telescope at this thing and gathering data. Dr. Michelle Bannister, an astronomer at the University of Canterbury who specialises in outer solar system objects, describes it as controlled chaos that somehow worked. She tells me because you had professional observatories, university telescopes, even amateur astronomers with backyard setups all contributing data. No one was in charge, but everyone was coordinating through Slack channels and shared Google Docs. It was beautiful. In a weird way, science at its scrappy best. The initial phase focused on basics trajectory, velocity, composition, size. By September 10th, they had those nailed down, hyperbolic orbit confirmed, comet-like composition, about 500 meters across, moving at 87,000 MPa relative to the Sun. Then came October 19th and the quantum emissions, and everything changed. Suddenly this wasn't just another interstellar comet. This was potentially groundbreaking physics, or first contact, or both. Every major telescope on Earth started clearing their observation schedules. The Hubble Space Telescope, the European Southern Observatory's Very Large Telescope, the Keck telescopes in Hawaii, ALMA in Chile. If it could point at 3I/Atlas, it was pointing at 3I/Atlas. But here's the problem, even with the best telescopes on Earth. We're limited by what we can observe from 100 million miles away. We can measure light spectra. We can track position and velocity. We can look for radio emissions and infrared signatures. But we can't see details. We can't study the surface up close. We can't sample the material directly. For that, you need a probe. On October 25th, NASA's Jet Propulsion Laboratory runs preliminary calculations on what it would take to send a spacecraft to intercept 3I/Atlas. The numbers are brutal. The comet's moving at 87,000 mph and accelerating. It's already past Earth's orbit, heading outward. To catch it, you'd need a spacecraft capable of reaching similar velocities, which is way beyond anything we currently have operational. The fastest object humans have ever built is the Parker Solar Probe, which reached 364,000 mph using gravity assists from the Sun. But that was designed for a very specific trajectory. It can't just redirect to chase a comet. The New Horizons probe, which flew past Pluto, is travelling at about 36,000 mph. Too slow. Even if you could magically turn it around and point it at 3I/Atlas, you'd never catch up. So you'd need to build something new. Launch it on a trajectory that uses gravity assists to build velocity. Then intercept 3I/Atlas somewhere beyond Mars' orbit before it gets too far out. JPL estimates minimum mission time 8 months from launch to intercept. Cost $2.50 to $3 billion. Probability of success 60%, assuming everything goes perfectly and Congress approves funding immediately. Congress does not approve funding immediately. What happens instead is more interesting. On November 3rd, SpaceX quietly starts running simulations, not officially contracted by NASA. Just Elon Musk being Elon Musk, deciding this is worth investigating on his own dime. By November 10th, they have a proposal, a modified Starship vehicle launched on a high-energy trajectory, carrying a smaller probe that deploys during a high-speed flyby of 3I/Atlas. The probe wouldn't land or match velocity that's impossible with current technology, but it could pass within a few hundred kilometers, taking high-resolution images and spectroscopic measurements during the encounter. Total flyby time may be 30 seconds, but 30 seconds of close-range data is better than months of long-distance observation. Estimated cost $800 million. Timeline launch by March 2025 to intercept in September 2025. NASA's response is lukewarm. They're not saying no, but they're not writing checks either. Too risky, too expensive, too uncertain. Then on January 7th, the anonymous $500 million donation appears. Suddenly the economics change. If private money covers most of the cost, and SpaceX is willing to eat some of the expense as R&D for future interplanetary missions, maybe this becomes feasible. As of January 15th, negotiations are ongoing. No final decision yet, but the clock is ticking. Every day of delay makes the mission harder, the trajectory less favourable, the required delta V higher. Dr. Alan Stern, principal investigator for the New Horizons mission, weighs in publicly. We sent a probe to Pluto, we visited a primordial object in the Kuiper Belt. Those missions took 10 years of planning. We don't have 10 years for 3I/Atlas. We have months, but that doesn't mean it's impossible. It means we need to move fast and accept higher risk. Sometimes in science, you get one chance. This is one of those times. Meanwhile, ground-based observations continue around the clock. The Atacama Large Millimeter Array in Chile, basically 66 radio telescopes working together as one giant telescope, is mapping the comet's molecular emissions with unprecedented detail. They're finding weird isotope ratios, deuterium levels that don't match any known comet population, carbon-13 abundances that suggest formation in a very cold, very old molecular cloud. Dr. Stephanie Millam from NASA's Goddard Space Flight Center analyzes the ALMA data and publishes preliminary results on January 18th. The deuterium to hydrogen ratio is 3 times higher than what we see in Oort cloud comets. This is consistent with formation in the interstellar medium rather than in any planetary system. 3I/Atlas might be pristine material from the early galaxy, unchanged for billions of years. Think about that. This object might have formed when the universe was 1/10 its current age. It might have been drifting through space since before Earth existed, accumulating cosmic damage, being shaped by forces we barely understand. And now it's passing through our neighbourhood, giving us a glimpse of deep time, of conditions that no longer exist anywhere nearby. But the quantum emissions remain unexplained. The isotope ratios don't account for that. The chemical composition doesn't explain it. Every classical analysis comes back saying, yeah, it's a really old, really weird comet, but nothing here suggests time-reversed quantum effects, which means either the quantum stuff is a separate, unrelated phenomenon, or there's something about the comet we're not detecting. On January 20th, the Breakthrough Listen team announces results from their active transmission attempt. They beamed a radio signal toward 3I/Atlas on January 15th using FAST, the Chinese radio telescope, a simple message, prime numbers, mathematical constants, a schematic of the solar system. If 3I/Atlas could respond via radio and did so immediately, the return signal would arrive around January 16th. Nothing. Dead silence. They waited 48 hours, thinking maybe there's processing delay, maybe whatever's inside, if anything's inside, needs time to decode and formulate a response. Still nothing. Dr. Andrew Simeon, leader of Breakthrough Listen, is careful in his statement. Absence of a radio response doesn't rule out artificial origin. It's possible our signal was too weak, or used the wrong frequency, or wasn't recognized as communication, or there's nothing there to respond. We simply don't know. But privately, sources tell me the team is disappointed. They were hoping for something. Anything. A change in the quantum pulse pattern. A radio burst. Some acknowledgement that the message was received. The universe remained stubbornly silent. Meanwhile, amateur astronomers are making contributions that surprise everyone. A high school science teacher in Arizona named David Copeland, using a homemade spectrograph attached to an 8-inch telescope, detects a faint emission line that the professional observations missed. It's at 656.3 nanometers, the hydrogen alpha line, normally super common in astronomical objects. But the line from 3I/Atlas is Doppler shifted in a weird way. It suggests hydrogen atoms are being accelerated to high velocities in a very localized region of the comet's coma. Copeland posts his findings on an amateur astronomy forum. Within 24 hours, 3 professional astronomers have confirmed it with bigger telescopes. Within 48 hours, there's a paper submitted to the astrophysical journal Letters citing his discovery. Dr. Frank Marcus from the SETI Institute tracks Copeland down for an interview. This is what I love about astronomy. You don't need a billion-dollar telescope to contribute. You need curiosity, decent equipment, and the willingness to look carefully at what everyone else is ignoring. David found something because he was looking at a wavelength range the professionals had already covered and dismissed as uninteresting. Sometimes fresh eyes see what experienced eyes miss. The hydrogen acceleration is another puzzle piece. What's causing it outgassing doesn't produce velocities this high. Neither does solar-wind interaction. You'd need some kind of concentrated energy release a jet, a plume, or something actively expelling material like a propulsion system. I'm not saying it is. I'm saying that's what the data looks like. And nobody has a natural explanation that fits. By January 25th, 3I/Atlas is 180 million miles from Earth and receding at about 2 million miles per day. It's still visible to large telescopes, but the quantum emissions are getting harder to detect. The signal-to-noise ratio is dropping as distance increases. Teams are working around the clock to extract every bit of information before it becomes impossible. They're combining data from multiple telescopes using interferometry, essentially turning the entire Earth into one giant telescope by synchronizing observations. They're using machine learning algorithms to filter out noise and enhance signal. They're running every analysis technique in the book and inventing a few new ones. And they're finding patterns. Dr. Yuki Tanaka, the postdoc who first detected the quantum anomaly, publishes a bombshell preprint on January 27th. She's been analysing the 3.7-second pulse timing with extreme precision, looking for any deviation, any structure within the pulses that might indicate information encoding. She finds it. The pulses aren't perfectly uniform. There are tiny variations, microsecond-level differences in the timing that repeat in a pattern. The pattern has 1/679 elements before it repeats. 1/679. That's not random. That's 23 times 73. 2 prime numbers. It's the same number used in the famous Arecibo message sent toward the globular cluster M13 in 1974. That message was designed to be decoded as a 23 by 73 grid of pixels forming an image. Is 3I/Atlas using the same encoding scheme? Is someone out there familiar with how humans send messages? Or is this pareidolia pattern matching in noise? 1/679 isn't that special. If you analyse any sufficiently long sequence of numbers, you'll find patterns that seem meaningful but are actually statistical flukes. Tanaka is cautious. I'm not claiming this is a message. I'm reporting what I found. The pattern exists. Whether it means anything requires more analysis and independent confirmation. Within days, 3 other research groups confirm the pattern. It's real. The variation in pulse timing has a 1/679 element structure. But decoding it, that's another story. If you arrange the numbers in a 23 by 73 grid, do you get an image or map mathematical relationships? Or just noise that happens to have that periodicity? Teams try every encoding scheme they can think of. Binary, ternary, grayscale, colour, mathematical notation. Nothing jumps out. No obvious picture, no clear message. Maybe we're not interpreting it correctly. Maybe the encoding is more sophisticated than we're assuming. Or maybe, and this is the depressing possibility, there's no message at all. Just a natural quantum phenomenon that happens to produce periodic variations with no meaning whatsoever. On February 1st, the SpaceX mission proposal receives preliminary approval from NASA. Not full funding, but a green light to proceed with detailed planning. Launch window March 15th to April 1st. After that, the trajectory becomes unfavourable, and the mission is impossible with current technology. They have 6 weeks to finalise the design, build a probe, integrate it with Starship, run simulations, and launch. It's insane. It's probably impossible. But they're going to try, because this might be our only chance, not just to study 3I/Atlas, but to prove we can respond quickly to unexpected opportunities, to show that humanity can move fast when it matters. The probe design is simple necessarily so, given the time constraints, high-resolution cameras, spectrographs, magnetometers, a particle detector to sample the coma, and one experimental instrument, a quantum entanglement sensor designed to detect and characterize the quantum emissions at close range. If everything works, if the launch succeeds, if the trajectory is accurate, if the probe survives the high-speed flyby, we'll get 30 seconds of data. 30 seconds to answer questions we've been asking for 4 months. It's not enough, but it's what we have. And while engineers scramble to build a probe, while astronomers continue observing from Earth, while physicists argue about interpretations and implications, 3I/Atlas continues its journey outward, indifferent, silent, mysterious. In 6 months, it'll be beyond Neptune's orbit. In a year, beyond the Kuiper Belt. In 5 years, it'll exit the heliosphere, the bubble of space dominated by the sun's influence, and return to the interstellar medium from which it came. And unless we send that probe, unless we catch up in the next few months, all we'll have are telescopic observations and unanswered questions. But even if the probe mission fails, even if 3I/Atlas disappears without giving up its secrets, something has changed. We've been forced to confront possibilities we weren't ready for. We've had to ask whether we're alone, whether physics is complete, whether reality is stranger than our models admit. And those questions don't go away just because the object that raised them does. So what's the bigger picture here? What does 3I/Atlas tell us about the universe we live in? And more importantly, what does it tell us about how much we're missing retrocausally? Here's something that should terrify you. We almost missed 3I/Atlas entirely. The Atlas Survey Telescope that detected it on September 5th, it was scanning that particular patch of sky by chance. The telescope rotates through different regions, looking for asteroids that might threaten Earth. If 3I/Atlas had passed through 2 weeks earlier, or if its trajectory had been slightly different, or if clouds had obscured the view that night, we might never have known it was there. It would have silently entered our solar system, swung past the sun, and disappeared back into interstellar space without humanity ever realizing anything unusual had occurred. Think about that for a second. The most significant astronomical object we've detected in decades, possibly ever, was discovered by accident while looking for something else entirely. How many others have we missed, Doctor? Avilob poses this question in nearly every interview. We've confirmed 3 interstellar objects in all of human history. 3, but statistical models suggest dozens, maybe hundreds, pass through the solar system every year. Most are small, faint, moving too fast to detect with current technology. We're essentially flying blind. In 2017, a study by researchers at Harvard estimated that at any given moment, there might be 10,000 interstellar objects within Neptune's orbit. 10,000, and we've detected 3. That's not a detection problem, that's a surveillance problem. Our telescopes are good, don't get me wrong. The technology for finding objects in space has improved dramatically over the past few decades. We can now detect asteroids a few meters across millions of miles away. We're getting better at this, but better isn't the same as adequate. The sky is vast. Interstellar objects are small, dark, and fast. By the time they're close enough to Earth to be easily detected, they're already on their way out. We're trying to spot speeding bullets in a dark room using a flashlight that only illuminates a tiny corner. And that's just visible light detection. What about objects that don't reflect much sunlight? What about objects coated in organic tholins that make them dark as charcoal? What about objects using stealth technology, if we're entertaining the artificial hypothesis specifically designed not to be noticed? On February 3rd, the International Astronomical Union's Minor Planet Center releases a statistical analysis that makes the situation clearer. Based on the detection rates of Oumuamua, 2I/Borisov, and 3I/Atlas, and accounting for observational bias and detection efficiency, they estimate the true rate of interstellar objects passing through the inner solar system. The number approximately 12 to 15 per year with diameters larger than 100 meters, 12 to 15 every single year, and we're catching maybe one every 2 to 3 years. That's a 95% miss rate. Dr. Robert Werrick, who discovered both Oumuamua and 3I/Atlas, puts it bluntly in an interview with Nature. We're missing almost everything, and the objects we do detect, we only spot them on their way out. We don't see them coming, we see them leaving. By the time we notice they're interstellar, they've already made their closest approach to the sun and are accelerating away. This isn't just an academic problem. This is a fundamental gap in our understanding of what's passing through our cosmic neighbourhood. If 3I/Atlas is natural, just a comet doing weird quantum things because of exotic physics we don't understand, then every other interstellar object we're missing could be teaching us something equally important about the universe. We're letting cosmic laboratories fly past unexamined. And if 3I/Atlas is artificial, if it's a probe or a message or some kind of technology, then we have to ask how many others have already passed through without us noticing. Maybe Oumuamua wasn't the first. Maybe it was the 10th or the 100th. Maybe there have been deliberate attempts at contact that we completely missed because we weren't looking carefully enough. That possibility keeps SETI researchers awake at night. Doctor. Jill Tarter tells me, for 60 years we've been listening for radio signals, assuming that's how aliens would announce themselves. But what if they've been sending physical probes instead, robotic explorers that pass through star systems, observe, maybe try to communicate in ways we're not equipped to detect? We wouldn't know. We'd be deaf and blind to it. There's a concept in information theory called the detection window, the period during which a signal is strong enough to be detected above background noise. For radio signals travelling across interstellar space, that window might last years, decades, even centuries depending on the signal strength. But for a physical object passing through the solar system at 87,000 mph, the detection window is months. Maybe weeks for smaller objects. Blink and you miss it. And we're blinking a lot. The solution seems obvious. Build more telescopes, build better telescopes, survey the entire sky continuously instead of in segments. Use AI to flag anomalies in real time instead of relying on human astronomers to notice things in data days or weeks later. That's exactly what's being proposed. On February 8th, the Vera C. Rubin Observatory in Chile announces it will begin operations ahead of schedule, specifically to improve interstellar object detection. The Rubin Observatory has been under construction for over a decade. It's equipped with the largest digital camera ever built for astronomy, 3.2 billion pixels. It will photograph the entire visible sky every few nights, generating 20 terabytes of data per night. Most importantly, it has automated pipelines that compare new images to previous observations within hours, flagging anything that moved or changed. If an interstellar object passes through while Rubin is operational, we'll know about it within 24 hours instead of days or weeks. First light is scheduled for May 2025. By June, it should be operational. But even Rubin Observatory has limitations. It's in Chile, so it only sees the southern sky. It observes invisible light, so objects that are very dark or very far away might still slip past. And it's one telescope. Granted, an incredible telescope, but still just one. What we really need is a network. NASA's proposed NEO-Surveyor mission, NEO, stands for Near-Earth Object, was designed to find asteroids that might threaten Earth. But the same technology can detect interstellar objects. NEO-Surveyor would operate in infrared from space, spotting objects by their heat signature rather than reflected light. The problem, it's not funded yet. Launch date keeps slipping, currently scheduled for 2028, but that's optimistic. By 2028, 3I/Atlas will be 15 billion miles away, far beyond the orbit of Pluto, completely undetectable. Whatever we're going to learn from it, we need to learn now. This is the frustration. We have the technology to do better. We have the knowledge to build detection systems that would catch virtually every interstellar object that passes through. We just don't have the funding, the coordination, or the sense of urgency until now. Maybe 3I/Atlas has changed the conversation when astronomers propose new surveys, new telescopes, better coordination. Politicians and funding agencies are actually listening, because it's not just about finding rocks in space anymore. It's about finding potential evidence of new physics, maybe even first contact. The Breakthrough Listen project, funded by tech billionaire Yuri Milner, announces on February 10th a $50 million initiative to develop AI systems specifically designed to detect anomalous objects in astronomical data. They're partnering with machine learning labs at MIT and Stanford to train neural networks on simulated interstellar objects, teaching the AI what to look for. The goal: deploy the system across multiple existing telescopes by the end of 2025, creating an early warning network that flags anything unusual within hours of detection. It's a start. It's not enough, but it's a start. Meanwhile, amateur astronomers are stepping up in unexpected ways. There's a movement now, a grassroots effort coordinated through online forums and Discord servers to point backyard telescopes at regions of sky that professional observatories can't cover. Thousands of amateur astronomers, each with modest equipment, collectively providing 24/7 sky coverage that complements the big professional surveys. They're finding things, not interstellar objects yet, but near-Earth asteroids that slipped through the cracks. Variable stars behaving strangely. Faint comets that hadn't been catalogued. Doctor. Michelle Bannister calls it distributed astronomy. She tells me the professionals have bigger telescopes, better equipment, more expertise. But the amateurs have numbers and dedication. Someone in Australia watches the sky while someone in Europe sleeps. Someone in North America takes over from there. You get continuous coverage that no single observatory can match. And if there's another 3I/Atlas, another interstellar visitor doing something impossible, odds are decent that an amateur will spot it first, or at least contribute crucial early observations. But here's the darker question: what if the miss rate isn't random? What if we're systematically missing certain types of objects? Imagine you're an advanced civilization wanting to explore the galaxy. You send out probes, millions of them, maybe billions programmed to pass through star systems and observe. But you don't want every probe detected. Maybe you want to test how observant a civilization is before revealing yourself. So you design most probes to be stealthy, difficult to spot, and you include a few that are deliberately obvious, that practically scream "look at me" to anyone with decent telescopes. The obvious ones are the test. Can they detect us? Can they recognize something artificial? Can they respond appropriately if they pass the test? Maybe then you make contact. Maybe then you send something less ambiguous. And if they fail the test, if they miss the obvious probe, or detect it but dismiss it as natural, then you mark that civilization as not ready yet and move on. I'm not saying this is what's happening. I'm saying this is a hypothesis that fits the data. 3 interstellar objects detected, all with unusual properties, all raising questions about whether they're natural or artificial. And we're arguing about it. running simulations, building probes to investigate. Maybe that's exactly the response someone is looking for. Or maybe I've been staring at quantum mechanics papers too long and I'm seeing patterns in randomness. That's also possible. Likely, even. But here's what's not speculation. We're missing most of what passes through our solar system. That's statistical fact. And every object we miss is a missed opportunity to learn something about the universe. If there are quantum anomalies happening on other interstellar objects, natural phenomena that could revolutionize physics, we're not seeing them. If there are genuine artificial probes passing through, we're not detecting them. If there are resources, or dangers, or wonders drifting past in the darkness, we're blind to them. That needs to change. The good news is that technology improves exponentially. The telescopes we'll have in 10 years will make today's instruments look primitive. AI is getting better at pattern recognition. Detection algorithms are becoming more sophisticated. Space-based observatories are becoming cheaper to launch. In 20 years, we might have comprehensive surveillance of the inner solar system. We might catch every interstellar object, track every anomaly, investigate every mystery as it happens instead of after the fact. But 20 years is a long time, and 3I/Atlas is teaching us that sometimes you only get one chance. On February 12th, a philosopher named Dr. Anders Sandberg from Oxford publishes an essay that goes viral in scientific circles. He asks a simple question: what is the universe trying to tell us that we're not hearing? His argument: the universe is full of information. Every photon, every particle, every gravitational wave carries data about where it came from and what happened to it. We're swimming in cosmic messages, constantly bombarded by information about the nature of reality. But we're only paying attention to a tiny fraction of it. We look at the wavelengths we understand. We measure the phenomena we expect. We filter out everything else as noise. What if the most important discoveries aren't hiding in obscure corners of space, but are right in front of us, encoded in data we're already collecting but not analysing correctly? What if 3I/Atlas isn't special because it's rare, but because we finally noticed it? Sandberg writes, every generation of scientists believes they're close to understanding everything, and every generation is humbled by the next. We are not different. We have sophisticated theories and precise measurements, but we're still children playing with instruments we barely comprehend, in a universe far stranger than we imagine. It's a sobering thought, and it's hard to argue with, given what we've seen over the past 4 months. So where does that leave us? We have one interstellar object that defies explanation. We have detection systems that miss 95% of what passes through. We have theories that don't quite fit the data, and we have a narrow window of opportunity closing fast. The SpaceX probe launches in 4 weeks if everything goes according to plan. It'll reach 3I/Atlas in September. We'll get 30 seconds of close-range observations. And then we wait for the next one, and the next one after that. And we hope that each new visitor teaches us something, brings us one step closer to understanding what's really out there. Because make no mistake, this isn't the end of the story. This is the beginning. 3I/Atlas is showing us how much we don't know, how much we're missing, how much further we have to go. And that ultimately might be the most important discovery of all. So what happens next? Where do we go from here? And why should you, sitting wherever you are, living your normal life, actually care about a comet doing weird quantum things millions of miles away? Retry KM. Let's talk about March 18th, 2025. That's the date SpaceX is targeting for launch. Assuming funding clears, assuming the probe is ready, assuming weather cooperates, and 1,000 other things don't go wrong. If the launch succeeds, the probe will spend 6 months chasing 3I/Atlas across the solar system. using gravity assists from Venus and Earth to build velocity. On September 14th, 2025, it'll scream past the comet at a relative velocity of 40,000 ph. 30 seconds of observation. High-resolution cameras clicking away. Spectrographs analysing composition. The quantum entanglement sensor, assuming it works, measuring those impossible emissions up close. 30 seconds to answer questions we've been asking for a year. Doctor. Sarah Seeger, an astrophysicist at MIT who's advising on the mission, puts it in perspective. We'll learn more in those 30 seconds than in 6 months of ground-based observation. But it's still not enough. We need hours, days. We need to match velocity, orbit alongside it, deploy landers if possible. But that's beyond our current technology, so we take what we can get. The data will download over the following days. First the high-priority science data, the quantum measurements, the close-range spectra, then the imagery, then everything else. By late September, we'll know what 3I/Atlas looks like up close. And then we'll spend years arguing about what it means. That's how science works. The observation is quick. The analysis takes forever. Competing theories gives endless peer review. Conferences where physicists politely destroy each other's hypotheses, eventually, maybe, consensus emerges, or maybe it doesn't. Maybe 3I/Atlas joins a long list of cosmic mysteries we've detected but never fully explained. Like the wow signal, the famous radio burst detected in 1977 that lasted 72 seconds, matched the characteristics of an intelligent transmission, and was never detected again despite decades of follow-up observations. We still don't know what caused it. Natural phenomenon, alien beacon equipment glitch. The debate continues nearly 50 years later. 3I/Atlas might become the 21st century's wow signal. The thing everyone talks about. The thing that launched 1,000 research papers. But never quite gets resolved. I hope not. I hope the probe gives us definitive answers. But hope isn't a scientific strategy. Meanwhile, preparations are underway for the next interstellar visitor. On February 15th, NASA announces the Interstellar Object Rapid Response Protocol, IORP, which everyone immediately starts pronouncing as IORP. It's a framework for coordinating international observations whenever an interstellar object is detected. The protocol designates specific observatories as primary responders. Within 6 hours of detection, they drop whatever they're doing and point at the object. Within 12 hours, secondary facilities join in. Within 24 hours, space-based telescopes are retasked if possible. Within 48 hours, there's a coordinated observation plan covering all available wavelengths and detection methods. The goal: never again miss the early stages of an interstellar visit. Never again scramble to organise observations while the object is already halfway through the system. Dr. Michael Kelly from the University of Maryland, who helped design the protocol, explains, "With Oumuamua, we lost critical time to organisational chaos. With 3I/Atlas, we did better, but still not great. Next time, and there will be a next time, we'll be ready from day one." The protocol also includes decision trees for when to attempt communication. If an object shows signs of artificial origin, regular pulses, anomalous acceleration, impossible chemistry, the protocol outlines who has authority to transmit messages and what kind of messages are appropriate. That last part is controversial. Some scientists argue we shouldn't broadcast anything without international consensus. You're announcing Earth's presence to unknown intelligences. That's not a decision a few astronomers should make unilaterally. Others counter that if an object is already in our solar system, it obviously knows we're here. Staying quiet is pointless. And if there's any chance of two-way communication before the object leaves, we can't afford to waste time in committee meetings. The protocol tries to split the difference low-risk transmissions' basic mathematical sequences. Representations of the solar system can be authorized by the IORP coordinator. High-risk transmissions detailed information about Earth, human biology. Our technological capabilities require approval from the United Nations Committee on the Peaceful Uses of Outer Space. It's bureaucratic, it's imperfect, but it's something. A framework that didn't exist before 3I/80less forced us to create one. Beyond the immediate science, beyond the probe mission and the observation protocols, there's a bigger shift happening. 3I/Atlas is changing how people think about humanity's place in the universe. For most of human history, Earth was the center of everything. The sun and stars revolved around us. We were special, chosen, the point of creation itself. Then Copernicus and Galileo showed us we're not the center. We're one planet among many, orbiting an ordinary star. Then we discovered our star is one of hundreds of billions in the Milky Way, and the Milky Way is one of hundreds of billions of galaxies. We're not special. We're cosmic dust on a rock circling a mediocre star in the suburbs of an average galaxy. That realization, the Copernican principle, the idea that Earth and humanity aren't privileged or central, has been brewing for 500 years. But it's remained somewhat abstract. Sure, the universe is vast. Sure, there are probably other planets, other civilizations, but we've never seen them. We've never had evidence. 3I/Atlas, regardless of what it turns out to be, makes it concrete. If it's natural, if comets from other star systems regularly pass through carrying physics we don't understand, then the universe is weirder and more complex than our theories suggest. We're not close to understanding everything. We're not even close to close. And if it's artificial, if there's intelligence out there, capable of sending objects between stars, manipulating quantum mechanics in ways we can barely measure, then we're not alone. We're not special. We're one species among potentially millions, and probably not the most advanced. Either way, it's humbling. Dr. Frank Drake, who wrote the famous Drake equation for estimating the number of civilizations in the galaxy, is 94 years old now. He's been searching for extraterrestrial intelligence since 1960. In a rare interview on February 20th, he's asked about 3I/Atlas. He says, "I've spent my entire career looking for a signal, a sign, anything that proves we're not alone. And now, maybe, just maybe, something has flown through our backyard doing things that shouldn't be possible. If this is first contact, even indirect, even just evidence that someone else is out there, then it's the most important discovery in human history. But even if it's not, even if it's just nature being strange, we've learned something fundamental. We don't know everything. There's mystery left. That's beautiful. There's wisdom in that. Whether 3I/Atlas is aliens or physics or both or neither, it reminds us that discovery isn't finished. The universe hasn't given up all its secrets. There are still frontiers. And here's why that matters to you. Personally, even if you're not an astronomer or physicist, every technology you use, your phone, your computer, GPS, medical imaging, solar panels exists because someone studied fundamental physics and found applications nobody expected. Quantum mechanics gave us transistors, lasers, and MRI machines. Relativity gave us GPS satellites that account for time dilation. Understanding electromagnetism gave us radio, television, and wireless internet. If 3I/Atlas leads to breakthroughs in quantum mechanics, if we figure out how to maintain coherence at large scales, or how to manipulate time symmetry, or how to extract energy from the quantum vacuum, the applications could be revolutionary. Quantum computers that work at room temperature. Communication systems that bypass the light speed limit. Energy sources that make fossil fuels and even fusion look primitive. Or maybe the breakthrough is philosophical rather than technological. Maybe learning that we're not alone or that the universe is stranger than we imagined changes how we think about ourselves, changes our priorities. makes our tribal conflicts seem petty in the context of a cosmos full of mysteries we've barely begun to explore. Dr. Carl Sagan, who died in 1996 but whose ideas remain influential, once said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." 3I/Atlas is the universe showing us something new about itself, something unexpected, something that demands we pay attention, ask questions, and accept that our current understanding is incomplete. That's not just important for scientists, that's important for everyone. On February 22nd, a high school student in Ohio named Emma Torres emails me. She's been following the 3I/Atlas story and has questions, smart questions, about quantum mechanics and time symmetry and what it means if particles can travel backwards. I spend an hour on a video call with her, explaining as best I can. At the end, she asks, "So we might find out we're not alone, like in my lifetime?" I tell her, maybe. We might find out this year, or in 10 years, or 50, or we might never find out, but we're asking the questions, and that matters. She thinks about that, then says, "I want to be part of it. I want to help look." And that's the real legacy of 3I/Atlas, regardless of what the probe finds in September. It's inspiring the next generation. Kids who are watching this unfold and thinking, "I want to be the one who discovers the next mystery. I want to be the one who figures it out." Science advances one generation at a time. The astronomers studying 3I/Atlas now were kids when Voyager flew past Jupiter and Saturn. They were inspired by those images, those discoveries, and they dedicated their lives to continuing the exploration. The kids watching 3I/Atlas now, they're the ones who'll design the missions to intercept interstellar objects in the 2040 S. They're the ones who'll build the quantum sensors sensitive enough to detect time-reversed particles from light years away. They're the ones who'll maybe, finally, answer the question, are we alone but we don't have to wait decades to take action? There are things you can do right now. If you're interested in astronomy, there are citizen science projects that need volunteers. Galaxy Zoo uses crowdsourced classification of galaxies to help astronomers study cosmic structure. Planet Hunters asks volunteers to analyze stellar brightness data looking for exoplanet transits. And there are projects specifically looking for anomalies, unusual objects, unexpected patterns, things that don't fit. Maybe you'll be the one who spots the next 3I/Atlas. Stranger things have happened. If you're a student, consider studying physics, astronomy, or engineering. We need people who can build better telescopes, write smarter algorithms, design faster spacecraft. The challenges ahead require expertise across dozens of fields. And if you're just someone who finds this interesting, talk about it, ask questions, support funding for space exploration and basic research. Vote for politicians who understand that science isn't a luxury, it's an investment in the future. Because here's the thing, 3I/Atlas is showing us that the universe is full of surprises. Objects we've never seen before, phenomena we don't understand, possibilities we haven't imagined. But detecting those surprises requires instruments. Understanding them requires research. Acting on them requires resources and coordination and vision. That doesn't happen automatically. It happens because people decide it's worth doing. So what happens next with 3I/Atlas March 18th launch? If everything goes according to plan, September 14th flyby, 30 seconds of data collection, late September initial data analysis. First papers published, October through December detailed analysis. Competing theories, academic arguments, 2026 follow-up observations by next-generation telescopes, attempts to detect similar phenomena on other objects, 2027 and beyond applications of whatever we learn, new missions, new technologies, new questions, and somewhere in that timeline, maybe we get an answer. Maybe the probe data definitively shows this is natural quantum effects in exotic environments. Or maybe it shows unmistakable signs of artificial origin, and everything changes. Or maybe, and this is the most likely outcome, we get more data but not complete answers. We learn something, but not everything. The mystery deepens even as we solve pieces of it. That's okay. That's how discovery works. You don't go from ignorance to complete understanding in one step. You make progress incrementally, each observation refining your theories, each experiment ruling out possibilities. 3I/Atlas is one step. An important step, maybe a huge step, but not the final step. There will be other interstellar visitors. With the Rubin Observatory coming online, with better detection protocols, with international cooperation improving, we'll catch more of them. We'll study them more thoroughly. We'll learn. And gradually, piece by piece, we'll figure out what the hell is going on. On February 28th, I receive an email from Dr. Yuki Tanaka, the postdoc who first detected the quantum anomaly. She's been analysing data non-stop for 4 months. She's exhausted. But she's also exhilarated. She writes, "Whatever 3I/Atlas is, it's reminded me why I became an astronomer. Not to catalogue known objects or refine measurements, to find something new, something that makes me question what I thought I knew. I don't know if we'll ever fully understand this object, but I'm grateful we noticed it. I'm grateful we're trying." That gratitude, that sense of wonder, that willingness to embrace mystery rather than fear it, that's what science is really about. We live in an age where we can watch this unfold in real time. You're not reading about 3I/Atlas in a history book decades after the fact. You're experiencing the discovery as it happens. You're watching scientists race to gather data, argue about interpretations, build missions to investigate. This is history happening right now. And you're part of it, just by paying attention. So keep watching the sky, keep asking questions, keep demanding that we explore, that we investigate, that we push the boundaries of what we know. Because somewhere out there, moving at 87,000 miles per hour, carrying secrets we've only begun to glimpse, 3I/Atlas continues its journey through the darkness between stars. It came from somewhere we can barely imagine. It's going somewhere we'll never see. But for a brief moment, a cosmic eye blink, it passed through our neighbourhood. It showed us something impossible, and it reminded us that the universe is vast, strange, and full of wonders we're only beginning to discover. And honestly, that's pretty damn exciting. Thanks for coming on this journey with me. Keep your eyes on the stars, and who knows, maybe the next impossible thing the universe shows us, you'll be the one to spot it first. Now, if you found this story as mind-bending as I did, go ahead and like this video if you haven't already, subscribe for more deep dives into cosmic mysteries, and drop a comment telling me, do you think 3I/Atlas is natural or artificial? What's your gut telling you? I'll see you in the next one. Until then, keep looking up